Hello everyone, we're Group 2 and we're going to present the case 94, which is the broadcasting the Olympic Games. For the case facts, the management of WBC Television Network has been celebrating for days. After several unsuccessful attempts in recent decades, they finally have hit the big jackpot. They have won the bidding war to gain the rights to broadcast the next Summer Olympic Games. However, reality also is setting in for WBC management. Telecasting the entire Olympic Games will be an enormously complex task. Many different sporting events will be occurring simultaneously in far-flung venues. An unprecedented amount of live television and live on the internet coverage of the various sporting events needs to be planned. Now for the problem, WBC must upgrade its private computer network to handle a significant bandwidth required for transmitting Olympic Games coverage from the event site to its home studios. The games will take place near Node A, while WBC's home studios are located at Node G. During peak times, the transmission will demand a bandwidth of 35 gigabytes from Node A to Node G. WBC can distribute the transmission across multiple network paths, provided the bandwidth on each link does not exceed its capacity. For the question A, by utilizing the entire computer network, what is the maximum bandwidth available in gigabytes for transmission from the general site of the Olympic Games to the home studios?
Before I explain the solution to this problem, we must first understand what the colors in Excel indicate. The cells highlighted in blue represent the information given on the case. The cells highlighted in yellow represent the variable cells. The cells highlighted in orange represent the set objective or the value being solved. The cells that aren't highlighted represent the cells that require formulas. The main formula used here is SUMIF, open parentheses, from node flow, close parentheses, minus SUMIF, open parentheses, to node flow, close parentheses. So the cells that are under from and to represent all of the possibilities that can be made to go from point A, which is from, to point B, which is to. Cells that are under from are positive, and cells that are under to are negative. The cells highlighted under flow are the ones that are optimal for each node to determine either the maximum or minimum flow. The sign used to highlight the relationship between the flow and existing capacity is less than or equal to, because existing capacity is the maximum resources that are available, while flow is the optimal amount needed. The cells highlighted under existing capacity are the values readily available for every possibility. The cells highlighted under nodes are all of the options that have many different combinations that can be either present in from, and, or to. The cells under net flow are pretty straightforward. This is the total amount of all the possible combinations that are done under the flow cells. An example of a positive net flow would be node A. There are three instances where node A is present, namely A to B, which is 13, A to C, which is 6, and A to D, which is 8. An example of a zero net flow would be node D. There are four instances where node D is present, namely B to D, which is 1, B to E, which is 5, B to F, which is 7, and A to B, which is negative 13. An example of a negative net flow would be node G. There are three instances where node G is present, namely D to G, which is negative 12, E to G, which is negative 6, and F to G, which is negative 9. Now the problem is asking for the maximum bandwidth, meaning the node that would have the positive net flow, which is node A. Therefore, the answer is node A with a maximum bandwidth of 27. So that's all for this problem. Thank you for listening.
So let us now discuss the case constraints and parameters. So let us discuss the case A. As we can see here, the first constraint is net flow should be equal to supply and demand. Each node's net flow is calculated to ensure the balance between incoming and outgoing flow. Node A supplies the total bandwidth, the positive net flow, while node G demands the total bandwidth, which is the negative flow. Intermediate nodes must have a net flow of 0. This ensures the maximum bandwidth for transmission is determined without exceeding the capacity of any link.
So for case question number 1, by utilizing the entire computer network, what is the maximum bandwidth available in gigabytes for transmission from the general site of the Olympic Games, which is node A, to the home studios, which is node G. So the maximum bandwidth available for transmission from the Olympic Games site, which is node A, to the home studios, which is node G, using the existing network infrastructure is 27 gigabytes, according to the result. So this was determined through a maximum flow analysis that evaluated the capacity constraints on each network segment. The bottlenecks in the network, particularly on key segments such as D to G and E to G, restricted the overall flow into node G, which serves as the final destination. The analysis confirmed that the existing network's capacity is insufficient to handle a higher bandwidth demand, such as the peak requirement of 35 gigabytes, making it necessary to explore network expansion options to meet higher demands.
For question B, WBC would like to expand the capacity of the network so it can handle the peak requirement of 35 gigabytes from the Olympic site A to the home studios G. WBC can increase the capacity of each link of the computer network by installing additional fiber optic cables. The next table shows the existing capacity of each network segment in gigabytes, the maximum additional capacity that can be added in gigabytes, and the cost to increase the capacity in millions of dollars per unit gigabytes added. Make a copy of the spreadsheet model used to solve Part A and make any revisions necessary to solve this new problem of handling the peak requirement of 35 gigabytes. Okay, so in Part A, the model was built to calculate the maximum bandwidth from node A to node G using the existing capacities of the network. For Part B of the case study, the goal shifted to meeting a bandwidth requirement of 35 gigabytes from node A to node G, while minimizing the cost of expanding network capacity. Here's what changed. First, we've added new columns. We've added column J, which is the added capacity. This is a new decision variable solver used to determine how much additional capacity is required for each link. We've also added column L, which is the maximum additional capacity. This column lists the limits on how much each link's capacity can be increased. And then we've also added on column M the cost per additional gigabytes used. This shows the cost in millions of expanding each link's capacity by 1 gigabyte. So second, we've updated the capacity. In column F, the new capacity, this column now reflects the sum of existing capacity and the added capacity. For example, the capacity for the A to B link increased from 13 to 17 gigabytes because solver determined that 4 gigabytes of additional capacity was needed. And third, for the net flow, in column P, the SUMIF function for net flow now balances the requirement of 35 gigabytes from node A, which is the supply, and negative 35, which is at node G, which is the demand, ensuring the total flow meets the new requirement. And lastly, for the solver objective, the objective cell used the sum product formula to calculate the total cost of capacity expansion by multiplying the added capacity and by the cost per gigabytes for each link. Solver was set to minimize this total cost. And now for us to solve part B, I set the following parameters in the solver. For the objective, we've minimized the total cost of capacity expansion calculated with the sum product formula. For our decision variables, we have the added capacity to calculate how much additional capacity is needed. And lastly, for the constraints, first we have added capacity is less than or equal to maximum additional capacity, which limits the expansion for each link to its allowed maximum. And second, we have flow is less than or equal to the new capacity. This ensures that the total flow on each link does not exceed the new capacity. And lastly, for the net flow, we have the net flow, which is equals to the supply and demand. This ensures the network meets the supply and demand requirements with 35 gigabytes from node A to node G. And so, after running solver, the total cost of capacity expansion was $34.4 million, which meets the bandwidth requirement of 35 gigabytes. The flow on each link was optimized to values like 17, 8, 10, and so on. Additional capacity was only added where necessary, such as 4 gigabytes on the A to B link and 5 gigabytes on the D to G link. This revised model ensures that the network can handle the Olympic broadcast while minimizing costs. I hope this explanation clarifies how the model evolved and how Solver helped us achieve the optimal solution. Thank you for listening.